I'm Ziwei Ji from UIUC, and I'm going to present our work, Characterizing the Implicit Bias via a primal-dual analysis, a joint work with my advisor Matus Telgarsky. Here is an overview of this talk. We analyze the implicit bias of gradient descent. The motivation is that, in practice, gradient descent can often find simple solutions with good generalization. This raises many natural questions such as, what are these simple solutions, and can we find them faster? In this work, we consider linear classifiers, but our result can also work for kernel methods such as the neural tangent kernel. First, we give a primal-dual proof technique for the implicit bias, and I will also mention that this proof technique can also be useful in deep learning. Second, while prior results are mostly focused on exponentially-tailed losses, we give a characterization of the implicit bias for a large class of general decreasing losses. Third, we prove fast margin maximization and implicit bias rates for the exponential loss, and specifically 1/t rates, while prior rates are 1/t at best. Okay, so this is an overview of this talk, and next I'm going to describe the setting of this work. As mentioned before, we consider linear classifier, which is very simple, but is still related to many important methods such as boosting and kernel methods, including the neural tangent kernel. We also assume linear separability, meaning that given a training set with inputs xi and labels yi, we assume there exists a linear classifier u, which can output the same sign as yi on every xi. Of course, our results can also be applied to the linearly separable case with NTK features or with other RKHS features. We consider decreasing losses, which is just a decreasing function L applied to y times the inner product between x and w. So minimizing this loss would force x times w to have the same sign as y as a true label. We also need to make a few other assumptions on a loss function. These assumptions are complicated, but here are some examples which we can handle. As usual, we can handle exponentially-tailed losses such as the exponential loss or logistic loss. We can also handle polynomially-tailed losses such as d to the minus k. We run standard gradient descent on the empirical risk R hat, which is just the average loss over the training set. Okay, as mentioned before, we study the implicit bias of gradient descent. If we use an exponentially-tailed loss, then it was proved by Sergey et al. That gradient descent will converge to the L2 max margin direction. I will formally define the L2 margin later, but here is a very simple two-dimensional example where the blue points denote the positive examples and the red points denote the negative examples. In this case, the max margin direction is just given by -2, 0, and indeed, if we run gradient descent, it will converge to this direction. However, the convergence rate to the max margin direction for gradient descent is very slow. It is only 1/log(t). And if we use a non-exponentially-tailed loss, then gradient descent may not converge to the max margin direction. So next, I'm going to describe our results. First, for the exponential loss, we prove 1/t margin maximization and implicit bias rates, while prior rates are 1/t at best. And then I will briefly discuss our primal-dual proof technique, and I will also show that using this proof technique, we can characterize the implicit bias for a large group of general decreasing losses. Okay, so here is the formal definition of normalized margin of a linear classifier W. It is just the minimum of yi times the inner product between xi and w, normalized by the L2 norm of w. We also call the numerator the unnormalized margin of w. The L2 max margin gamma bar is just defined as the maximum possible normalized margin that could be achieved by unit vector. And we can also show that there is a unique L2 max margin solution denoted by U bar. Here is our main result. If we start from 0 initialization, and if we use only for simplicity, And if we use an aggressive step size, which is given by the inverse empirical risk, then gradient descent can maximize the margin at a variable t rate. Moreover, for almost all training data, the normalized gradient descent rate given by Wt over the L2 norm of Wt also converges to the L2 max margin solution at a variable t rate. Here is the comparison with prior results. So first of all, for most prior first-order hard margin SVM solvers, the margin rates are variable sqrt, including normalized perceptron, boosting, and steepest descent. We can also run Nestor's accelerated method on a certain variable epsilon smooth approximation of the margin function for the boosting problem. And this would require O variable epsilon iterations, so kind of a variable t rate. However, then we will need to run an additional smoothing step on potentially different levels of epsilon. And moreover, even if we have a variable t margin rate, it only implies a variable sqrt implicit bias rate. And in this work, we have to use some special ideas to further prove variable t implicit bias rate. So to sum up, the very simple algorithm of logistic regression and gradient descent can already yield the current fastest first-order hard margin SVM solver. Okay, so next I'm going to briefly discuss our primal-dual proof technique and give a characterization of the implicit bias for general decreasing losses. Let me first recall prior analysis, which is based on the primal. So we let Pt denote the level of correctness, where Pti is just given by the I unnormalized margin, yi times the inner product between xi and wt. Moreover, we define this crucial function psi, which is just L inverse applied to the sum of L of Pti. In other words, L inverse applied to the total loss at step t. So prior analysis can prove variable sqrt margin maximization rates using this function psi, and specifically they use two crucial properties of psi. First, they use the fact that psi is L infinity smooth. For example, for the exponential loss, psi is just the log sum x function, which is one smooth with respect to the L infinity norm. Second, psi can approximate the true unnormalized margin up to an additive error of log n. In our work, we further introduce a dual analysis. Given Pt, we can define the corresponding dual variable Qt as the gradient of psi at Pt. For the exponential loss, it is just the softmax function applied to minus Pt. The key observation is that update from Qt to Qt plus 1 is actually a mere descent update with entropy regularizer on the dual objective function g defined here. It is the square of the L2 norm of the sum of qi, yi, xi. So we prove that G is L1 smooth, which allows us to prove the fast variable t rates. And the reason is that the reason prior can only prove variable sqrt rates is that they only use the smoothness of the primal objective, but we use smoothness of both the primal and the dual. Also, a general version of G in a nonlinear homogeneous setting can also allow us prove a general property called alignment. It was proved in our Europe's paper from last year, and it means that we can show the gradient descent rate Wt and minus gradient of the empirical risk. Also, they both converge to the same direction. So we can see that this primal-dual proof technique can also be useful in deep learning. And another application of this technique is to characterize the implicit bias for general decreasing losses. So here is just the definition of G, and let's still first consider the exponential loss. In this case, if we define Q bar as the minimizer of G, then we can prove that the sum of Q bar I, yi, xi is equal to gamma bar U bar. On the other hand, the implicit bias of gradient descent, which is the limit of the normalized gradient descent rate, is also given by the L2 max margin solution U bar. In other words, in this case, the implicit bias of gradient descent can just be characterized by the dual optimal solution Q bar. And this is actually true in general for both exponentially-tailed losses, such as the exponential loss and logistic loss, and for other losses, such as the polynomially-tailed losses. And specifically, we can prove that the implicit bias of gradient descent, the limit of the normalized gradient descent rate, is also given by the direction of the sum of Q bar I, yi, xi. Okay, that's all for this talk, and I'm happy to take any question.